I'm here. I'm here and I'm okay. I just couldn't get things synced up. But here I am. How's everybody? Okay, I'm just looking at your view, and you can't really see that very well. So today I wanted to start with chapter 4, unit 4, unless anybody has any questions about regression. And we can work with regression over the next few weeks because you're going to have a test at the beginning of November, your second test. So I thought I'd introduce probability today and then finish it next week, and then we can just do problems for a week. Review problems for the test. So are there any questions about regression? I want you to work with the materials I gave you, work on the exercises. You have to read all the notes, right? I'm not going to read through them online. I think it's pretty self-explanatory. You just have to sit and read through them, read through the exercises. This document here is in the probability section, Unit 4 Prob, and it's called Overview. You can pull it out of Moodle, or you can just work with me here. And what I want to do with this document is an overview of probability, what you need to know, what we're going to get into. It covers the results of probability rules. And by putting everything on one sheet, I'm hoping that you can compare and contrast the concepts and understand them better. Now we have an intuition for probability. You've probably taken probability before, or you've seen diagrams like these. These Venn diagrams are taught in grade school. If you've not seen them, maybe you missed class that day because they don't spend too much time on it. But the idea is about relationships and outcomes and understanding relationships in different settings. So I just want to review these and at the same time introduce the rules, which, like I mentioned, I think they're pretty intuitive. There's just a couple of places where people lack the intuition, and I want to clarify concepts there when we get there. So, any questions so far? Any comments on my decision to just go ahead to probability? Okay. All right, no comments. All right, so here we have two events in this set of all possible outcomes. Okay, so S stands for the sample space. So S stands for sample space. And it represents all the possible outcomes. Do you want me to give you a minute so you can print up this document? Okay, no comment. All right. So what does this tell us? There's two possible outcomes and only two. So if you know that A occurs, you know you're here, that means that B could not have occurred. Okay, so there's a couple of things I've told you. There's only two possible outcomes, and if one occurs, the other one cannot occur, given the way I've drawn this. So you could think about this, an example would be, you could say deal or no deal. So this could be the event of a deal, and this could be the event of no deal, okay? Or you could say rain or no rain. Okay, so it's just that they're complementary, we say. These are complementary events. So if I assigned a probability and I said event A has a chance a 30% chance of occurring, what can we say about these probabilities? So what can we derive from knowing that the chance of A is 30%? First, what is the chance of A and B happening? So let's take a moment to discuss what that means. This is if both happen at the same time, and also written as like this, also known as an intersection of events. So the probability, so this diagram doesn't necessarily tell you the probabilities. I mean, you could draw it to scale, but the point of drawing it is to show the relationship between them. And then given any kind of values, you can make some inferences. So if chance of A is 30%, what's the chance of A and B? How would we figure that out? First, we need the chance of B. Let's write that down. The chance of B would be what if A is 30%? So let's see your intuition for solving these types of problems. So what do you think? Just take a guess. Without us discussing probability, you can do most of this document. You can complete it. That's right. So your intuition is good, Edgar. So it's going to be 70% because A and B are complementary. That means that the chance of A plus the chance of B makes 1. Okay, so that's what complementary would imply. It implies all these things, but that's one. Okay, so your intuition is good. To find one from the other, you just do 1 minus. So to calculate the chance of B, what you did was take the chance of A I'll just make it smaller. Okay, I'll make it bigger here. So what you did to calculate that is you knew A, so that is right? So you computed 1 minus probability of A, because together they make 1. So now, back to what we were doing. So what's the chance of A and B occurring if 2 events are complementary? The document is in probability, in answer to your question, and it's called Overview. It should be in Moodle. It should be in Moodle. If you don't find it in Moodle, there's a version of it in the notes for probability. Oh, I have to find, hold on, I'm just getting the, okay, I'm back. Okay, so you can get this in the probability notes as well. My file. There it is. Oh, it's taking a bit to open. Okay, let's just work with this. So anyway, everybody sees this or has this? If you have the probability notes, you'll find it in there too. Okay, so we were saying the probability of A and B refers to the intersection of them. When do they occur together? What's the chance that both can occur at the same time, or where they both occur at the same time? Well, in this case, because they're complementary, it means only one of them can occur. So the chance that they occur at the same time is moot. There's no chance. The answer is 0. Okay? What about the next question? A or B. Or is also represented with a U for union. And we think about the chance of one thing or another thing happening. What's the chance of A or B? So I could be here, or I could be here. Those are the only possible events. So together, to compute this would be probability of A plus probability of B. So or becomes a plus in a very specific case. All right? And in this case, complementary events, it's always going to be 1. It doesn't even matter that I know what the probabilities are. I know that the total, the sum, will be 1. Or 100%. All right, and then we have the event not A or B. So now I'm going to introduce the concept of not. Well, we had an idea of that over here. A is the same as not B. B is the same as not A. Okay? Because what is not? So in red I'm making notes. So not means so for instance, the probability of AC or A complement is the same as writing the probability of not A, and that's the same as 1 minus probability of A. And this happens to be the probability of B. I could also write that without probabilities. I could just say AC is, I could also say AC is equal to not A is equal to B in this case. Okay? These are all the same thing. So finally, where is not A or B? So this whole thing, the whole sample space, is the event A or B. So there is no not A or B. So if we were to write this mathematically, this would be 1 minus probability of A or B, because it says not, and I'm going to follow the rule of not, right? But it turns out for complementary events, A or B was 1. Oh, I was supposed to do this in blue. Wait, let me do this in blue. Oh, that's okay, I'll finish. So 1 minus 1 means that this will be 0. So there is no place where either A or B happens. It's either A or B and nothing else. I think that's the way to think about it, okay? So whenever I say not, when I say not, you should be thinking or I'll say some other event. And that never happens, so there's no chance of it happening, so it's 0. So there's different ways to write this, but they're all synonymous. All right, you ready for the next one? So we've just described the implications of complementary events. Complementary events are the only things that are possible, the only events that are possible. And together, they make up all possible outcomes, the entire sample space. So the probability of A or B, and there could be others, I could have more in there, but the probability of any of the complementary events happening is equal to 100%. the chance of, so that's here, the chance of them happening at the same time does not exist. It's 0. And the chance of anything else happening does not exist. It's 0. Okay? So I could have done all of this without knowing the probability of B. Even though I calculated it here, I didn't even need it. Okay, so that's complementary events. Let's now talk about what are known as disjoint events, or mutually exclusive events. Okay, so here are two events that are mutually exclusive. It demonstrates that A could happen, B could happen, or what are we going to call this? Say something else. Anything else, that's right, something else is out there. There could be other events, but we're not focused on there. But the point is, how do we express this in terms of A and B? We say not A or B. Okay, so I could actually write that up. I can write that down so that you know. So this event out here is called not A or B. So if you go, so I'm going to explain this and use this example later. If you go to a salon, a beauty salon, you could have a haircut, you could have a manicure, and you can have other things as well out here. Okay, that's how we could define that. So these are mutually exclusive events, and I want to solve for these different probabilities. Oops. Given the information. So I'm telling you A's chance is 30%, B's chance is 40%. What's the chance of both happening at the same time? Remembering A and B means where they intersect. Where does that happen? Do they ever intersect? No, they never intersect. There's no intersection. So this will have to be 0 as well. So it's similar to complementary events in that way. What about or? Or means one or the other. So either if I'm here or here, what's the chance of being here or here? The chance of being an A is 30% and B is 40%. So what's the answer? Okay, so you have intuition, just add them, right? So when it's A or B, A plus B But again, this is only in a specific case. This is only happening, we're only able to do this because these events are disjoint. Okay, so this property of adding, we did it here, but we also did it here. Well, in both cases, they never overlapped. Okay, there was no place that A and B occurred together, so we're able to just add them. So I'm going to make a note that this is just true for disjoint events. That you can just add. The same here. So by writing that, you can see now that complementary events are disjoint. You see? Complementary events are disjoint. But disjoint events are not complementary. These do not complete the entire space. They do not represent all the possible outcomes. So there's something else. What is the chance of something else is the next question. We're going to use the same property as we did before, 1 minus probability of A or B, right? Because the not makes us go 1 minus. And we already know what A or B is. It was 70%, so then I just plug that in. So the chance of something else is 30%. So you could draw on here. You could say this is 0.3, this is 0.4, and this is 0.3. Which is helpful. It can be helpful when things get unruly, because I could put another event in there. Okay, so everything's good so far. So this should feel fine. You feel confident, right? And this is intuitive. So what if the events overlap? Okay, so I'm going to make this large enough. You're not going to be able to see all of them, but there you go. So now the events are overlapping. I left the probabilities the same. Let's see, how do our answers change? Well, now we have an intersection. Now we have an area where they overlap. So there are events, there's an event known as A and B. There's still, we could calculate A or B, but that's going to change as well because we have to take account of this overlap. And as far as not A or B, there's still a something else. So let's see. I'll give you a couple minutes to answer these questions, and then I'll ask you to give me the answers. If the screen gets blurry, remember to just refresh or reload the page. Okay, I'm back. The overlap is A and B. That's the overlap. It's called A and B. And I tell you what A is, and I tell you what B's chance is. And I also tell you what A and B's chance is. So you already have the answer. The chance of A and B is 10%. Now, if I didn't give it to you, you would not know what it was. Okay, there's no way of knowing if events are overlapping. There's no way of knowing what that intersection would be. And maybe you're doubting and you're feeling like, oh, that's not true, I can figure it out. Actually, you cannot figure that out. So your intuition is failing you here. Okay? If you thought that. If I don't give it to you, you don't know what it is. But now that you have it, you can figure out this one. What's the chance of A or B? Well, Well, the events are not disjoint, so you can't just add A and B. In fact, you can't add A and B because if you add this area or this chance with this chance, you see you're double counting this place where they happen together. So what we have to do when events are not disjoint is use what's known as the general rule and say the chance of A plus the chance of B plus, minus the chance of A and B. This is the general rule for disjoint event, for events. The general addition rule. So that turns out to be A of 30%, A of 30%, B of 40% minus the overlap of 10% gives 60%. Yes. And finally, we can also figure out the something else. Out here, that's going to be 1 minus the chance of A or B. So that's 1 minus the 60% to give you 40%. Okay? So we did this. We were able to do this because I gave you that. Otherwise, it would not be possible. And I will make my point clear when I show you the next example. Any questions about that one? So this is for the case of overlapping events. So we covered complementary, disjoint, and overlapping. And for overlapping events, you have to have this extra information here. Or you can't solve. All right, finally. So if you're a little bit rattled, now what do? What are independent events? See if you can solve the different probabilities given these events are independent. And I'll discuss independence in a second, but first I want to appeal to your intuition. Let's see how your intuition serves you. Or if it doesn't, we can correct your intuition. Okay, let me give you a couple minutes. How you doing? What'd you get? Okay, so the first question asks you for A and B, so you need the intersection. Now last time I gave it to you, but this time I didn't give it to you. Instead, I told you the events are independent. What does independence mean? Independence is distinct from the other things I've mentioned, but it looks like overlapping. So independent events overlap. But they're more than that. There's a criteria, there's a relationship between A and B that you need to understand. The chance of A and B is not 30%, Hector. But thank you for trying. Does anybody want to think about this a little bit more before I explain this? So it looks identical, well, identical, but it's overlapping just like this one is overlapping, but you're told they're independent events. So what does that mean? It means that I will write it in red because my rules are going in red. The occurrence, am I spelling that wrong? Occurrence, I have to check. My spelling has gone since I started learning Spanish. Okay, it's 2 R's. The occur. Okay, so that in this sense, we can, because there's 2 events, the occurrence of one event does not change the probability of the other. So it means, I'll try this several ways to make it clear, but right now A, the chance of A happening is 30%, right? But let's say B happens. So let's say we know we're in B. And we happen to be in A2. For A and B to be independent, it means that the chance of A within this subsection doesn't change. The chance of A is still 30%. So it mathematically, or in symbols, it means that the probability of A given, so that means given, that B happens, that's conditional probability. So if B happens, the chance of A is equal to the chance of A. Just because B happened, it doesn't change anything. Now that's not necessarily the case. Let's say A was, for instance, hold on, okay, so let's say A is a manicure. I'm trying to make this seamless with the rest of the notes. So let's say this is a manicure in a salon. And B is hair color. And at the salon, there are other services that can be purchased. So in the salon, let's say we're observing individuals who've gone into the salon, and a random person who's had a hair color, right? What's their chance of having a manicure? Now let's say a person's already spent money on a hair color. Will that change? It could possibly change the chance of them wanting to have something else done, right? Because they've spent money. If you're told the events are independent, it means that the chance of a manicure would still be 30%. No effect of having had the hair color done. Okay, so you can see how I've described it. You can debate whether that's going to be a set of independent events, but if you were told they're independent, that's how it would work. Now, how does that affect the calculations? Well, first of all, let me step back to tell you what this is. This is called the conditional probability. And this represents the word given, like it already happened. So B happens, what's the chance of A? For conditional probabilities, for independent events, it doesn't matter. And how does that affect the calculations? It turns out more in general, let me write this in general. I'll use the same. In general, the probability So the probability of both of these events happening at the same time would be the probability that B happens, and of those times, given B, in other words, the probability of A. And that's also equal to, I could also write it like this. So in general, that's true. And I've been giving you, because of these special cases in the problems above, you never saw this yet. I never showed you this. But this is, in general, A and B is equal to the probability of B happening times, of those times, what's the chance A happens? You would multiply them. But it turns out that for complementary and disjoint events, this would be 0 and it would make the whole thing 0, okay? And this would be 0 and it would make the whole thing 0, because there's nowhere that B happens and also A happens when B happens, okay? In the above, over here, if I didn't give this to you, you would have had to figure out, you would have had to find this A given B calculation. Or you would have had to find out B given A, okay? But you didn't have to do that because I gave you the result. So what do we do here? We could do either one. You're going to get the same answer. This is the general property, but then any of these just reduce to, it doesn't matter that B happened. So all that ends up coming of this is multiplication. This is just going to be A times B, however you look at it. The conditional for independent events drops out. So think about that for a second, or a minute or so. So that's why your intuition, some of you will have the intuition to multiply those numbers, and this is why. Because for independent events, the occurrence of one event does not change the probability that the other happened. So the conditional probability is the same as the probability originally, and the general interpretation reduces to just A times B. So for independent events, you multiply the probabilities to find the probability of this and that. So far, if events are independent, you multiply, but from above, if events are disjoint, remember, independence is not disjoint. It's a different concept. Sounds similar, but different, okay? Independent does not mean disjoint. In fact, that's why I show you this, to tell you, no, independent events overlap. That's right. So hopefully you can review this video if you still didn't get it, and you'll get it later. This is really important. Out of this whole sheet, this is the only place where students struggle. And I'll spend some more time discussing this. So let's finish this. So A times B is 12%. I have nowhere to put this. So this is going to be, or let's write it. I'm going to put it a little bit higher. I'm going to put this a little bit higher. Okay? So now we can solve the rest. For A or B, it should be probability of A plus the probability of B minus the overlapping piece, because otherwise, no, that's not A and B. That's the overlapping piece. And so you get 30% plus 40% minus the overlapping piece, which is 12%. I can put it in there for you. Okay? So that's 56. And finally, what's the chance of other services? What's the chance of being out here? The chance of being out there is 1 minus A or B. So this is equal to 1 minus 56% is equal to not 56, it's 58, isn't it? 58. So then this one would be $42. Sorry for that miscalculation. Right, 58%. Okay? So, you have a better maybe idea that's distinguishing these concepts. Maybe you're still unsure about the independent case. So you can read in the notes. I put some more comments about that. This is basically an overview. And I guess I'll take any questions you have. Everything's on this page. I've put everything, almost everything about probabilities on this page. We're going to go a little deeper to understanding the concepts in a bit. Any questions? Okay, so let me get the notes. All right, it's going to take a while, it said. Okay. So, although I've been talking about probabilities until now, talking about using them when we were discussing normal distributions, uniform distributions, we want to, just like I've used the probability rules and reviewed them with you, I want to go through and develop probability rules with you, and then develop the theory so that we can use it for estimation, computing estimates, and then also use it to make inferences about a population given a sample. Okay, so we're going to take samples and calculate estimates, and then we're going to use a sample to say something or to say something significant about the population, not just to calculate statistics. We're going to talk about how good those statistics are at telling us something about the population. All right. So first I want to I did spend some time working in the overview with your intuition, and I want to do that a little bit more. Okay, what I want to talk about are random events. Okay, that's different from deterministic events. Events where you know their outcome. For example, you know if you have no fuel in your car, you're going to run out of gas, and the car will stop. random events, you don't know the outcome. However, because you know the possible outcomes of some random events, you can make predictions. So let's begin, and we're going to use this example throughout this unit. When you flip a coin, you know it could come up heads or tails. You don't know which one will come up, but you have an idea that it will have a chance, we say 50% chance that it'll come up heads, and a 50% chance it will come up tails. Where do we get that idea from? Where do we get that idea from? Let's say you have a nephew or a young cousin, and they tell you that they've been flipping a coin hundreds of times, and every time they flip the coin, they record whether they had a head or a tail. Okay? This is a graph that could be made of this kind of a thing, where you flip it once and you record. In this case, the person got a head, so this is heads here. So it's 100%, so 1 out of 1 was heads. So it's 100% heads. So here, on 4 flips, 2 were heads out of 4. So that was 50%. So that got plotted here, you see? So let's say your nephew flipped, let's just say, well, I'll say off of this example. Now these are just flips of a coin. Here's 1, 2, 3, 4, 5, 6, and it's been contracted, right, to show you this, because this is much, you could stretch this out much more. So let's say he flipped 100 times, and it turns out that he had sorry. $70 tails and 30 heads. With 70 tails and 30 heads, he tells you, well, it looks like I'm having 30% heads. Why is it not 50%? Shouldn't it be 50% chance? Shouldn't it be out of so many times I'm going to get 50% tails and 50% heads? It didn't happen. What would be your answer to explain to him what's wrong? How would you ratify or explain why he's not getting 50%? What would you tell him to do? idea. I've shown you, I've demonstrated using this chart so that you see the answer. You need to tell your nephew or your cousin to keep flipping. Keep flipping. Not until about here is there a steady state. Okay, after about, I don't know what that is, maybe, 200 flips, it stabilizes and it's like 50-50. Okay? So what you see here, this is called long run, the long run. In so many tries, in so many tries, and it's from phenomena to phenomena, the number of tries required would differ. In terms of flipping a coin, it takes over 200 for the long run to demonstrate the chance of 50-50. So we think of probability, now we can define probability in this way as long run relative frequency, okay? Because we're taking the percentage of so many flips, right? So this is 2 of 4, this was 1 of 1, and here would be 100 out of 200. So this is what probability is. The probability is the same as the long run relative frequency. To actually demonstrate outcomes, you'd have to consider the possibility in the long run. Okay. The relative frequency probability is the limit of the proportion of times that event A occurs in a large number of trials, N. And how many you need to be able to see that probability depends on the situation. The probability is the limit as N becomes large or approaches infinity. Because notice, after that point, after some threshold, it just stabilizes. It's a steady state and it's consistent. And I have to specify that each repetition is independent. Aha. So flipping a coin is the classic case of independent events. From sequential flips, from flip to flip, each time I flip, the probabilities don't change, you see? So when you think about independence, always you can fall back on that concept of flipping sequential flips of a coin. I'll say outcome of sequential flips of a coin. Okay? So we refer to two events or compounding events because an event can consist of many things. Anyway, they can call A could be, anyway, I'll get into that in a bit. So event A and B are independent if knowing that the outcome A occurs does not influence the probability that B occurs. So now I'm repeating myself. Similarly, a trial is independent if the outcome of one trial does not influence the outcome of any other. So, some clarifications. That's right, Jasmine. Okay, so when people say, or you see advertisements about cancer striking 1 in 2 men and 1 in 3 women, that doesn't mean that out of a group of 3 women, 1 will get cancer, okay? What it means is if you have many women, so usually we're talking about populations, then %, which is 1 out of 3, in the long run. Okay? Okay, so you'd have to look at the larger population. So similarly, the figures, unfortunately, that we're watching right now are the accumulating number of cases of COVID. Now, cases, if you're going to compare from region to region or country to country, you should be comparing those in terms of rates per population size. And you would say something like, I think it's like 550 per million population in the US. Sorry, this would be COVID deaths. Something like that. Okay, so you wouldn't say, yeah, even it's probably hard to say that as it's not so meaningful. In terms of, in medical statistics, you always state things in the long run, okay? Okay, what if you flipped a coin twice? The outcome on the first trial does not influence the outcome on the second trial. Okay, so this is repeating what I said about flipping coins. Okay, so these trials would be independent. And then I have some other examples. Consider 4 differently colored M&Ms. Pick one randomly and eat it. If it's blue, then the next M&M you select to eat cannot possibly be blue because they were 4 differently colored M&Ms. Since the outcome of your first selection influences the outcome of the second, the trials are not considered independent. So the probabilities changed because I ate one of the M&Ms. So those are not independent events if you do not replace. So this is going to be called you refer to sampling without replacement. Are not independent events. If you were simple random sampling, those outcomes would be considered independent from, sorry, the outcome of the sample itself. What just happened? Uh-oh, I hit something. Oh no. No. Is this? I touched something. Okay. Sorry. No, I learned a new button. Where was I? So each simple random sample, the sample itself is independent from any other sample you could have drawn. Okay? Okay, so I want to talk about compound events. I'm going to lay out a few examples. Consider the experiment of flipping 4 coins. You can think about flipping them one beside the other, or one coin flipped 4 times. The possible outcomes are listed here. You could have had I'm trying to play with this button. No, I can't go bigger. Okay, anyway. So you could get ahead, the next one ahead, and head and head. Or you could get ahead, head, head, tails. These are all the possible outcomes here. And they are 12. Now a way to come up with that number without making the list is to realize in the first flip there's 2 possible outcomes. In the second flip there are 2 possible outcomes. In the third 2 are possible, and in the fourth 2 are possible. So if you multiply these, you can figure out that there's 12 possible outcomes. Sorry, not 12, 16. Oh, sorry. Yes, 2. 16 possible outcomes. All right. And what I've done is defined for you the random variable of interest, which is x. And x is the outcome of flipping 4 coins. So these are the simple events possible. These are all the possible events. I put them in curled brackets and call this the sample space. Now each outcome is equally likely. The chance of a head, so if I took just the first one, actually, you know what? I'll hold off on that description for a second. I'm going to do it simple. There are 16 possible outcomes. They all must be equally likely. Right? Because this was done randomly, they are each equally likely. So since there's 16, and the probability is equally likely, that must be 1. So that means the probability must be equal to 1 over 16. So the probability of each outcome is 1/16. If you remember, when I mentioned variable in the first class, a variable takes on values that are a number, okay? Now these are not numbers, obviously, but you could convert those to numbers. You could let H be 1, sorry, H be 0 and T be 1, and then you can translate all of these to numbers if you like. But you don't have to, okay? Because we know that's going to suffice as an outcome. All right, so that was my first example. Now what I want to do is I want to compound those simple events of all possible outcomes and redefine X as something else. X is now, we're going to say, the number of tails in 4 flips of a coin. And here are the possible outcomes: 0 tails, 1 tail, 2 tails, 3 tails, and 4 tails. And I'm going to separate all the outcomes above into the respective category. So 0 tails looks like this, but 1 tail can look like this, 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 or this. 2 tails can look like 6 different things, 6 different combinations, and then 3 tails like 4 different combinations, and 4 tails 1. All right, so those are compound events: 0, 1, 2, 3, and 4. Well, let's figure out the probabilities of those events. So notice how I write it. The probability of 0 tails can be written as, so I've defined X. So I'm using X as the variable, but I keep on defining, I continue to define it as different things, okay? So, so this would be, let's figure out what's the chance that X equals 0, which means no tails. The chance that X equals 0, well, there's only one way, and we know the probability of H, because we figured it out above, is 1 out of 16. So that means the probability of X equals 0 is 1 out of 16. Now, if this is the first time you've seen anything like this, and you did learn about the normal distribution, this equal sign might bother you. What we've just done is we've moved into discrete distribution territory. This is a discrete distribution where X can be 0, 1, 2, 3, 4. Only 5 possible outcomes, and that's it. That's different than the continuous distribution, like the normal distribution, where it can be infinitely many outcomes, okay? In discrete distributions, you can find the probability that the outcome is one of these. That's actually what we do. Questions? Now let's solve the rest. What's the probability X equals 1? Well, 1/16 for this one. This one's 1/16, 1/16, 1/16. They're all 1/16. So what is the probability that X equals 1? Right, so it should be 25% because what you're going to do is say probability of H, T plus, right? This is an example of or H, TH, or H, THH, or THHH. Right? It's either this or this or this or this. That's what you're figuring out. You're compounding them, and that's going to be 4/16 or 25%, 1/4. If you like fractions or decimals, it's whatever. I mean, you should be able to work with both of them, but for final answers and things, if you're going to write it as a decimal, use as many as 4 decimal places. You'll get the hang of it. But you should be able to work in both fractions and decimals. So finally, let's continue this. X equals 2. I won't do that again. I'll just add them up as 6/16. Right? You can reduce that to decimals. That would 0.375. The probability X equals 3 would be 1/4, just like the other. There's 4 out of 16, which is 1/4, or 0.25. And then X equals 4 is just 1/16. Got it? So now let's put these numbers over here. So I could write this in that way. I could write it in, this one like this. Here are my results. So I've put them on a line. What I've done here is made a table. Now this table is analogous to the normal distribution table in that you have the probabilities, you have the outcomes, but that's it. So, when we use a normal distribution, it was a distribution of percentiles, but for this distribution, the probabilities are just at a point. There's nothing in between those. So if I was to draw this, it would just be a spiked drawing. I'm going to do that, work with that later, but I can just, this would just be, well, no, I won't put it here. There's a reason why it's not here. But we could draw this later. We'll deal with that. And these are the possible outcomes. Again, this is a discrete distribution, so that's it. Now with this table, referring to it, where these are the possible outcomes for X, so I use little x, and these are the probabilities, we refer to this list as the probability distribution of X. And then we can use it to solve problems related to the variable X, the number of tails. Is that how I defined it? X is the number of tails, yes. Okay. So I can say, what's the chance of at least 2 tails? Well, at least 2 tails, if you think of the possible outcomes of the discrete distribution X could be 0, 1, 2, 3, 4. At least references 2, 3, or 4. Por lo menos, right? Por lo menos. And I could write it mathematically like this, greater than or equals to. Again, because it's discrete, the equals will make a difference. I'm going to include that as well. So to find that, this is X equals 2 plus x equals 3 plus x equals 4. And I add up all of those, this, and this. It's probably easier with the fractions, right? So 6, 10, 11, 11, 16. And you can put that in your calculator if you want. Six, 8, 7, 5. What if I asked you what's the chance of less than 3 tails, less than 3 tails is 0, 1, or 2. You notice I say the word or. So that's x equals 0 plus x equals 1 plus x equals 2. And again, this will be 11, 16 or 6, 8, 7, 5. Okay, so this is just an exercise. We derived the probability distribution and then we used it to answer questions. That's all we're going to do in this unit. We're going to develop or use probability theory to create a distribution for a problem at hand and then use that to answer questions about possible outcomes, to make estimates. So the last one, less than 1 tail or more than 3 tails, is just these two possible outcomes. I could write that mathematically like this. I just said less than 1 or greater than 3. So you get the idea now. When there's a less than or a greater than sign, it's really what we're saying is or. So this is probability x equals 0 plus probability x equals 4. So always reference, you know, the sample space when you do these problems, and that's what I did here. And I plucked out what I needed. So that will be 216. Okay. So to recap, an event is any collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. A compound event is any event combining 2 or more simple events. So we did all these things, right? I presented the events, we talked about the simple events, and then compounding them, putting them together like these. The sample space for a procedure consists of all possible simple events. Okay, so you guys can read that. Okay, we're going to review the probability rules one by one. There's 6 rules. The first rule, and again, you have intuition for all of this, but now we're going to formalize it. The probability of any event is between 0 and 1, correct? So the event A is between 0 and 1, and event B would be between 0 and 1, including 0 and 1. So we can write it like that. The second rule is that all possible outcomes together must have the probability 1. So we can write this as the probability of the sample space. Just note, sometimes I write in my notes PR and sometimes just P. They're the same thing. I just haven't I haven't made them consistent through the notes. Okay. The rule for complements, which we learned. Two events in general are complementary if only one of these two events can occur at any time. To write the complement, we can use a bar. Oh yeah, I didn't mention the bar. A bar, or say not a, or a complement. They all mean the same thing. So complementary events are disjoint. They don't overlap. They're mutually exclusive. But more than that, they're the only possible outcomes. So they're more than disjoint events. This is an extra criteria. And then I just gave you two examples related to the number of tails and 4 flips variable that we discussed. Rule number 4, we're already on rule number 4. Two events are disjoint if one of the events occurs at any time. They have no common outcome and so never occur simultaneously. In other words, they never overlap. It turns out that if A and B are disjoint, if I want to know the probability of A or B, I just have to add them. So that's a special rule for disjoint events. Just add if they're disjoint. And you want to know this or that. So we already applied that rule in the case of the event flipping 4 coins. And the variable number of tails and 4 flips. Okay. All right. So let me give you a minute or two. It's 8:15. Let me give you a minute or two. I'm going to get some water. Solve all these problems using the rules you know so far. Okay, you done? For this one, I would just draw it. There are two outcomes that are mentioned, and we'll assume they don't overlap, right? So A, this is very bumpy. Do that again. This is my sample space S. A is 48. B is 27. And something else would be 1 minus or 0.25. So now I can answer the questions. What is the probability that the doctor is not in the hospital? So A was doctor office. Okay, so this is office. And this is hospital. So the doctor is not in the hospital. Okay, so probability of not in the hospital is 1 minus B, so it's just 1 minus 0.27, which is .73. What is the probability that the doctor is either in his office or in the hospital? So probability of A or B. So that because they're disjoint, it's just A plus B probability. So we get 0.75. Very good. And then he didn't go to the office or the hospital. So this would be probability of not A or B. Okay, so this is either or in English, and this would be neither nor in English. So to solve this one, it's just 1 minus probability. Oh, what happened there? Very weird. Let's move it up. Like a reflection. One minus probability of A or B, so it's 1 minus 0.75, which we already saw from above is 0.25, and that's it. There it is. That's what I had pressed on the button. Okay. No questions? So that was easy. That was pretty easy. So just those are the first four rules. The fifth rule. So we already discussed this. This was the overview. This is the page I mentioned. It was in your notes. So you can transcribe, if you didn't before, you can transcribe the notes onto this page. That page was supposed to motivate the discussion about independent events. And I already explained this, so you guys can review this page. And here's my example. To draw it, to bring this home about independent events, the rule for independent events. Okay, don't worry about that part at the top. Okay, so our example. Consider if there are 10,000 women. I'm going to write it down. If there are 10,000 women where A is the event of a manicure and B is the event of hair coloring, observing women, these 10,000 who go to a salon, the chance of A is 30% and the chance of B is 40%. So I give you that information. This is given. So referring back to the overview, that's case 4, sorry, the typo. You are told to assume that A and B are independent. So if this scenario was this one with the salon, the question for what's the probability of A and B, what's the chance in 10,000 women? Well, it should be the same, right? The probability should manifest. Let's say 10,000 is enough, or it's the long run, right? Let's say 10,000 is enough to demonstrate the long run relative frequency. So in that case, out of 10,000 women, 30% would have a manicure. Since the events manicure and hair color are independent, then 40% of this subset of women, the 3,000, just like 40% overall, the probability doesn't change, also has their hair colored. So now you take the 3,000, the subset, times 40%, and so 1,200 women have both manicure and hair color. Okay, so this is showing using the population, using the long run relative frequency idea. So 1,200 out of 10,000 is 12%, which we could have just found by taking the probability of A times the probability of B. Now you could have done this the other way as well. You could have just said, take all 10,000 women, and how many of those women have their hair colored? Well, 40% of 10,000, or 4,000 women have their hair colored. And now out of those 4,000, how many also have a manicure? Well, we're told the events are independent, so just because women had their hair colored doesn't change the probability that they also have a manicure. So 30% still, just like overall, 30% of the subset also has a manicure. And you see, you get the same result. It doesn't matter which one you start with. It's still 12%. So let me just write this out the long way and we'll be done with it. Let me write this the long way. What I mean is, okay, so probability of A and B, I told you, is the probability of, okay, so manicure was A, right? times the probability of B given A. So this is what I figured out. The probability of A is the 30% that I applied to the 10,000. And then out of the ones who already have a manicure, the 3,000, I calculate the probability of B. Now, because they're independent, this is just times the probability of B. Nothing changes. It's still, it was 40% initially for B, so it's 40% even if A happens. And then alternately, we could also write this in the second exercise, where we take the hair color first, and then we say out of those times, what's the chance that they also have a manicure, but this just reduces to multiplying B times A. And in the end, they're just the same. Okay, so because of independence, this just becomes probability of B, and that one just becomes probability of A. So we assumed independence to do this. It's not necessarily true that they're independent, but let's say we had a bunch of evidence from data from past, and we found that it doesn't change. It doesn't change. Maybe it's because women have in this worldview, women have the intention to get both done, and they don't change once they've spent money on one. They could even have the services done simultaneously, in fact. And it won't matter because they'll spend the money at the end. Okay? Okay, so now try this one. Try this one without me. Okay, what I'm asking you to do is to display the Venn diagram for these events A and B that are compound events. Well, I've drawn from the list of possible outcomes for the variable number of tails and 4 flips. And I've demonstrated below what the outcomes look like. Two tails, looks like this. That's compound event A, observing two tails and 4 flips. Event B, observing less than 3 tails and 4 flips. So that could be 0 tails, 1 tail, or 2 tail. Now, how would you draw this? How would you draw these? What would be the relationship between these two? Are they disjoint? No, because they have an overlapping piece. But different from overlapping, this piece only resides inside of B. This actually is the only other drawing that we're going to talk about, other than working with 3 events. This is the only other drawing for 2 events. This would be B, and A would just be inside. So if we were to answer the same questions that we answered for the overview, if I ask you, what's the probability of A and B? What's the probability of A or B? And what's the probability of not A or B? What would you get? First of all, probability of A is 6/16, and probability of B was 11/16. If you remember, we calculated these before. So A and B would be the intersection where they share events. That would just happen to be A in this case. And the union of them, while the larger of the two is B, so if you're in A, you're already in B, so that's irrelevant. So we get, if we were to use the rule, we could not use the disjoint rule because they're not disjoint. We would have to take A plus B minus A and B. It's redundant. We're doing it twice. We're adding A and B and then subtracting A and B. Let's not even do it that way. I mean, we wouldn't get the wrong answer, but basically our answer is just B, right? So this looks different. It's a little bit different than the other ones, but you can find the answers once you draw the Venn diagram. So similarly to the other units, especially GDS, well, all the units, I tell you to draw things. Trying to pick them visually helps you a lot. And finally, 1 minus A or B, it would just be 1 minus probability of B. The outside, or the not, would just be this outside of B. Okay? So if you put the numbers down for all of these, this one would be 6/16. This one would be 11/16. And this one would be 5/16. And you would have gotten the wrong answer to finding this if you added A and B. If you didn't realize that this was included in here, they're not disjoint events. So I'm going to continue until page 12 because I want to finish this. If you have to go, I'll just say goodbye to you now, but I'm going to go to page 12. I started a half an hour late, so I need to end off somewhere that you have enough material. Well, anyway, at this point, if you have to go, you still have enough to get started. Read through these notes and try the exercises in the practice assignment. Next class, I'll finish off these notes, so you'll have all of probability done. We have to do Bayes' rule, and I have to teach you the rules of means and variances. Now, there's videos on all this stuff if you want to go ahead and work ahead. Among my stats videos, you can find probability. And I did, just trying to think. Anyway, you also have the quizzes online to practice. Okay, so let's see. Try this one. This is a little bit different because I have now two variables. So this is a joint distribution. Call this a joint distribution. So I'm showing you, demonstrating all the possible outcomes of gender and occupation class. Also, this is discrete because I can make a list. Whenever I can make a list, it's discrete. So each of these, like this one here, means that's the probability of being a woman and in class A. Okay, now these are all the possible outcomes, so, and they're disjoint. So the way I've written it, you can't be two things at the same time. More than two. You're either a male or a female, and either in one of these. So this would be your primary occupation class, I guess. Some people work two different jobs. Maybe they are in the service industry, but they're also an education. No, they're financial services, but they also are a professor. And that would put them in two different classes. But I've divided them, so this is primary occupation, let's say. So now, verify that this is a legitimate assignment of probability. So what I'm actually asking is find the probability of the sample space. So what you have to do is sum all the probabilities and make sure that they're 1. Okay? And it's true that they do sum to 1. Not sure what happened there. Okay, what's the probability that a worker is female? How do I figure that out? I would total all these probabilities to get the probability of a female. So what I'm doing is adding together the probability of woman and A plus the probability of woman and B all the way to adding the probability of woman and F. And when you add them all up, the chance of being a woman in this population is 40%. Next problem. What is the chance that a worker is not engaged in F? So F would be here, and you could calculate that to be 0.04. So you just add across genders. And then what we really want to find is the probability of not F. So probability of not F, we already learned that's 1 minus F. So that's 1 minus 0.04 or 0.96. So yes, 96%. And are we done? That's the last one. What's the chance that a worker is engaged in one of D or E? So probability of D or E is, because I told you they're all disjoint, D plus E, I can just add them, and I have to calculate them here first, right? So this one would be 0.14, and this would be 0.14. So it ends up being 0.14 plus 0.14, which is 0.28. Very good. And that's it. So now we're oriented around this distribution. We have an idea how it works. We understand what the elements are and how to combine them to find joint or compound events. Adding across to find the probability of women, which we figured out was 40%. And then I guess men must be 60%, right? So now the question is, using this distribution, our occupation A and being female independent events, how in the world do we answer that? Now you have to think, what does independent mean? In this setting, it's a good setting to use the concept of independence. So let's think about it. If we were sitting in the classroom and we were staring at the door and we were betting on the chance, so let's say this was a distribution of gender and occupation. So this is our distribution. And you had to bet on the occupation of the next person that comes in the occupation class of the next person that will come in the room. Now, which one seems more likely? This one was, let's see, this one was 4%. This one was 14. Oh, that looks really messy. And then this one was 17, and this one was 31, and this one was 20. Okay, so if you were to bet on the occupation of the next person in the room, the occupation class you would probably bet would be B, right? It's the highest. You have nothing else to go on. However, if it happens that the next person that appears, you can see a glimpse of the person approaching the classroom, and the person happens to be a male, will you switch your guess? That's the concept of independence. If you switch, then the events would not be independent. Okay? Because you're assuming the probabilities stay the same, whether you're male or not. But if you switch, what did I just say? If you don't switch, that means that they are independent. You think that they are independent. Okay, so let's see this problem with the numbers. Let's work with the numbers for female, and occupation A. So let's say if we saw somebody coming in, forget about the distribution even, just if we saw somebody coming in that was a male and the occupation classes were divided by like services, education, nursing, physicians, and it was divided like that. Now, disproportionately more women go into nursing than men. If one of the occupation classes was if one of the occupation classes was nursing and you saw a man coming in, the chance of you thinking that that person is a nurse goes down, right? Because you don't expect a guy to be a nurse. You could be wrong. My husband's a nurse, so, but in general, your odds are probably not a nurse. So your probabilities will change. So let's see what happens here with this. We don't know what A is exactly, but let's see how what the numbers tell us. A has a probability of 20%, and female has a probability, we said, of 40%. So the probability of A and female happens to be given, or woman, I'll call it woman. It's 8%. To be independent, I'm going to have to write the word woman or it's going to be confusing. A and woman, or woman. I wrote this so weird. So male and A and women are independent events if, I wrote if and only if. That means if and only if. That's my habit from studying mathematics. I should erase it though, because it might be confusing. If the probability of A and woman is equal to the probability of A times the probability of woman. Let me write that again. So what you have to do is check. So this is going to be the technique you're going to use. You're going to call this the left-hand side. So this is the left-hand side, right? A la izquierda. This is the left-hand side. The left-hand side we already know. That's just 0.708. That's already given to us. The right-hand side this is how you do a proof in mathematics. The right-hand side is equal to, well, PA was given as 20%, and probability of women, we calculated as 40%, which is equal to, we got the same thing. So since the left-hand side is equal or the same as, I use 3 lines for like equivalence, the same as right-hand side, then they are independent. All right, this is the approach to showing independence. You make it as though they are independent mathematically, and you check. So it turns out these are independent. So it's probably an occupation where gender doesn't matter. So maybe financial services, or maybe, I'm trying to think. Yeah, there's a lot of different genders in occupations. But anyway, so it's going to be in an occupation class that there's just as many, it's just as likely you're women as you're men. It doesn't matter. The gender will not change. Knowing the gender doesn't change the chance that they're in that occupation class. All right, so this is just a review of the Rule 5, the multiplication rule for independent events. If events are independent, to find the probability of their intersection, you just multiply the events' probabilities. That's all this says. And then we get on to the last rule. But first I just want to say, remember we write this, but because it doesn't matter that A happens, it doesn't change the probability of B. This reduces to this expression. So we make a concluding statement from the rules so far. The concluding statement is, in summary, probability of A or B, if you get that, add the probabilities if they're disjoint, and if you're asked about A and B, multiply probabilities only if they're independent. Only if they're independent. Don't just go off multiplying probabilities. You'd have to know that's true. And it might not be true, but if you did do that, you would be making an assumption. Okay, I want you to do this exercise. And then finally, the last rule, which we already discussed, so we did all of this. This is just bringing it all home. Bring it all together. The general addition rule for any two events. If you want to know the probability of A or B, you have to add the probabilities and minus the overlapping piece, and we already dealt with that. So we already dealt with this problem. Let's actually calculate A or B for this one. Let's do that. Oh no, because they're disjoint events, so it won't work. Okay, forget it. I'm going to go back on that. Oops. Because they're disjoint events, it doesn't matter. So anyway, we already used this rule. So now that's where I'm going to stop. That's page 12, and it is 9 o'clock. So thanks for sticking around. Those are the 6 rules. You should be able to work on the problems that I've called, I'm titled Try This, like this one, and the other ones. You can read ahead. I will discuss this next class, but you can read ahead. And then you can try this assignment for practice. The solutions are there. Solutions are there for almost everything. And see? And then there's another quiz here, so you can work on all this stuff. And then I'm going to spend some time on conditional probabilities and Bayes rule, and then finish the notes. So that's what we're going to work on next class. So you can work ahead, work on read the notes, work on the exercises in here, attempt the online quizzes, and we'll see you next class. Any questions? I'll stay back a few minutes if you have questions.